Chapter 12, Part 1, Gravity. So Newton's law of gravitation. Law of gravitation is a stating that every particle of matter attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So the force is proportional to the product of the mass of the two particles, and it is proportional to 1 over r squared, and this r squared is the distance between the two particles. The gravitational force can be expressed mathematically as f of g, or f of gravity, is g m1 m2 over r squared, where g is the gravitational constant. So in other words, if I have this type of relation, in order to make this proportionality an equal sign, instead of f being proportional to m1 times m2 and f being proportional to 1 over r squared, I can just write f equals a constant, in this case we call it capital G, m1 m2 r squared, where this g is a gravitational constant in our case. The other very important thing to talk about is that this is M1, this is M2. They don't necessarily have to have the same mass. And it applies to every two particle in the entire universe. For example, sun and a coffee cup that you have, they will apply some sort of a gravitational force to one another, okay? Even if the particles have very different masses, the gravitational force they exert on each other are equal in the strength. So f of the m1 to m2 will be equal to the f of the m2 to m1, okay? So any two particles attract one another, and they have the opposite directions for their forces, and they are always equal, kind of like action-reaction. So for two particles that have masses m1 and m2 and are separated by the distance r, the force has a magnitude given by this. F is capital G m1 m2 over r squared. And G is, as I just said, is the gravitational constant, which is 6.673 times 10 to the negative 11. Okay, so if I have m1 here and m2 here, this F is the F that m2 is applying to m1. So this is f of 2 to 1. And this negative f is the f that 1 is applying to 2. So 1 is applying to 2. All right. And the reason that we choose this to be negative f, because this direction is positive and this direction is negative. Okay. So let's go over this little example. The mass of the moon is 1 over 81 times of the mass of the Earth. Compared to the gravitational force that the Earth exerts on the moon, the gravitational force that the moon exerts on the Earth they should be equally strong. It does not matter what the masses are, m1 or here, for example, m2. The force that's been applied from one to the other due to gravity, so f of 2 to 1 or 21 and f of 1 to 2, they should have the equal value. So they should be equal. One is in the opposite direction of the other. Okay? So gravitational force on a large object. If you have any particles can be assumed to be a point particle. So as long as its masses is roughly distributed spherically about its center, okay, kind of like, you know, a sphere, a solid sphere. So we can think that this solid sphere here with a radius of r1 is just a point particle here with the same mass. m1 is here, m1 is here. And this sphere is acting like a point particle. And that point particle has all the masses concentrated on that point. Okay, so I can think of Earth being a point particle located at its center. I can think of Sun being a point particle located at its center. So, in other words, where the center of mass is. So, center of mass is where that point particle is located. Right, wherever that the center of mass is. So for example, here I have a sphere with radius r1 and a mass m1, and I have another sphere with a mass m2 and radius r2. I can think of this system as 2 point particles being separated in the same distance, same mass, and they will apply the same gravitational force to one another. So in other words, if I want to consider, for example, Sun and Earth, so if I say that this is Sun, and let's say that this is Earth, I can think of this system as a point particle here and a point particle here. Okay, so this is Sun and this is Earth, with the same relative distance from one another. But rather than having a sphere like that, I'm just showing it with a point particle. Okay, so we can think of each object as a point particle located at its center of mass. So let's go over one example here. Example number 1, determination of G of Earth. Consider a person positioned slightly above Earth's surface. Okay, use the gravitational force and the Newton's second law, okay, to determine the acceleration due to gravity. So in other words, we have a object, for example, of mass m, okay, and being above the Earth's surface, just a little bit maybe, above the Earth's surface. And then we would like to find the gravity of G due to the gravity of the Earth. So in other words, I am interested to find this G, to see what this G is. So we know that if I have a particle, then Earth would apply the force of gravity to it, and that force of gravity is F equals ma. If it's falling down, or if it's freely falling, then I have A being G, which we know what the value for that is, 9.81 meters per second square. Okay, so I have F equals mg, which we usually the book shows this with W, okay, which we know it as weight, is, by the way. So F equals mg. I know that this F is a force due to gravity from Earth to that object, or from Earth to that person. So it is also equals to G gravitational constants, the mass of the Earth, which is one of the particles or one of the masses, the mass of the person or object, and the radius between them. Okay, which if the person is close to the center of, to the close of the surface of the Earth, so close to, let me actually get rid of this F here. So close to Earth surface, R is just the R of the Earth, or the radius of the Earth. So then F is G, mass of the Earth, okay, mass of the object or person, and then R is the distance between the two objects, which in this case, close to the Earth's surface, is just R of Earth, or the radius of Earth. So these two should be equal, right? So they should be equal. In other words, I have mg being equal to G m of Earth m R of Earth squared. Now I can cancel out this m with this m from each side, and then I will be left with G being equal to capital G, which is the gravitational constant, mass of the Earth, okay, and radius of the Earth squared. So that's what the G is. If you substitute numbers for this, so for example, if you put G being equal to 6.67 times 10 to the negative 11, if you substitute whatever the mass of the Earth is, okay, whatever the radius of Earth is, which is, I think, 6,500 kilometers, if I'm not mistaken. But if you substitute these numbers, then your G will be equal to 9.81 meters per second square. So we know what the value for G is, and this value for G is pretty consistent, or pretty much constant. Gravitational attraction of spherical bodies and the acceleration of gravity decreases slowly, not much, with altitude. So if you're, let's say, way, away from the surface of the Earth, the average surface of the Earth, let's say that you're in the space shuttle, or you're in the International Space Station, you are higher than the average surface, or you are not around the surface of the Earth, in other words. Okay, so your R is greater than the radius of the Earth. Okay, so in other words, your R is not only the radius of the Earth, but you have also a height. For example, here for the space shuttle, you have 150 kilometers above the Earth's surface. So not only you have 6,400 or 500 kilometers, which is the radius of the Earth, but then you are actually at some height, which is, in this case for space shuttle, is 150, okay? So this would be your R. But the value for G, if you calculate the value for G, then this is actually, if you calculate the value for G, okay, this value of G is not really changing that much with respect to this R. So in other words, if I do this, I will have G as a constant here, M of E here, which is the mass of the Earth, and then R is just radius of the Earth plus your height, or the object height, squared. All right. So if you're pretty close to the surface, then this H is obviously 0, and you're getting G of 9.81. But if you're really, really high, this can cause you get a different value for G. Okay, but within 200 kilometers away from the surface of the Earth, the value for G should be pretty constant. It does not change that much. But if you go really away from the surface of the Earth, okay, so remember that G is capital G, M of E, and R squared, and this R is the radius of Earth plus the height, okay? So if height is 0, okay, in other words, you are at surface, then what happened is that the G value would be 9.81 meters per second squared, okay? If H is really, really big, or a high value, like 10,000 kilometers away, for example, okay, then you're really away from the surface of the Earth. Then the G will go to 0. And you can see it somehow around here, for example. If you are at the surface, if your height is 0, okay, if your height is 0, then the value associated with G, so if you're right here at height equals 0, you're at the surface of the Earth, okay, then the value for G is 9.81, close to 10. But if you're really away from the surface, let's say that you are about 20,000 miles away from the surface of the Earth, then the value for G is getting very close to 0. Okay, it will never be 0, but it will be really, really small. Okay, so if I have a, for example, geosynchronous satellite going, I don't know, with maybe 23,000 miles away, rotating around Earth, then that means that it will almost feel no G because it's really away from the Earth. So compared to the Earth, planet X has twice the mass and twice the radius. So planet X has twice the mass, so m of X is 2 of m of Earth, and radius of X is also 2 times of the radius of Earth. Okay, so compared to that, this means that compared to the Earth surface gravity, the surface gravity on planet X is, so let's see, the surface gravity was G m of E R of E squared, right? Or in our case, R here is R of E plus H, but since we're at the surface, this H is 0. Okay, so this is for Earth. Now, if you wanted to write it down for planet X, then G of X is, this is a gravitational constant anywhere in the universe. M of planet X, R of planet X squared, which means you have G, M of X is 2 M of E, and then R of X is 2 R of E squared. Okay, so then you have G of X being G, 2 M of E, and 4 R of E squared. And then what you have is that you can cancel out this 2 with this 4, and then you have 2 here. Okay, and then this is equal to G M of E R of E squared, but then you have 1 over 2 here, okay, because of this. So it means, and this, we know what this one is. This is the G of the Earth. So G of X is half of G. In other words, G of X is half of 9.81. Okay, so that's the answer. Another example, but this is more of a note, or very important note here at this point. The law of superposition states that the force on a particle is the sum of individual forces for every other particle, okay? So for example here, if I have a particle here at the center, okay, and I have 2 other particles, okay, at a specific distance. So this one will apply this force, F2, and this top particle will apply force F1. In other words, my particle at the center is experiencing 2 individual forces. I have F1 in this position and F2 in this position. And this 2 forces that are vectors will have a sum, okay, which I can show with vector F here. And this vector F is the actual force that my particle at the center will experience, okay? So I have to sum of all the forces, and they're all gravitational forces. They all have directions, okay? So F will be the sum of all the F's, for example, F1 plus F2 plus F3 and so on, okay? So I want to find the force due to, you know, gravity of these 2 other particles. So what I have is I have 3 particles here. The first thing I need to know is to know what this distance is because it's not given to us. I have 2 times 10 to the 12 meters. I have 2 times 10 to the 12 meters here. So I can easily find this length. So I have 2 times 10 to the 12 and 2 times 10 to the 12 here. And then I can find this x right there. So x is 2 times 10 to the 12 squared plus 2 times 10 to the 12 squared. So this would be 2 times 10 to the 12 times the square root of 2. Okay, so this would be that distance from this particle to here. So I'm just going to call it x. Okay, once you have that, you can find F1 being G M1 M x squared, okay? And then you can find F2, which is G M2 M R squared. And once you do that, okay, you have F1 and F2, then the sum of those, so then F1 plus F2 is F1 squared plus F2 squared plus 2F1 F2 cosine of theta, okay, or cosine of the angle between them. I don't want to show it with theta because I don't want you to confuse this theta with the theta being shown in the figure. So let's call this alpha maybe. So this would be the total force. In other words, if you have individual forces, you have to add them up to find the total force. So let's call and talk about the Kepler's law of orbital motion. Johannes Kepler, was a very bright guy, okay, and he was looking at the naked eye observations of Tycho, and Tycho made the most accurate naked eye observations down to the precision of 1 arc minute and with a naked eye. And so what Johannes Kepler did was he was trying to make sense of Tycho's observations with a fully circular orbits of planets. So he was using a perfect circle with no eccentricity at all, okay? A perfect circle in theory, and kind of makes sense of the Tycho's observations of the planet's orbits. But then there was an error of about 8 arc minute between the theoretical values, considering the perfect circle, and with the Tycho's observations or experimental values, okay? So there was a 8 arc minute disparity, okay? Or an error between the actual observations and the theory, okay? And so Johannes Kepler wrote down some laws in order to explain what the orbital motion should be. So in his first law, he said the planets follow elliptical orbits with the sun at one of the focus points, okay? And elliptical orbits are not only circulars. So if you have a full circle, a perfect circle, then the eccentricity is 0. But the eccentricity could be anything other than 0, okay? For example, for a planet or a comet or an asteroid, you can see that this orbit could be very elliptical. It's not a perfect circle. And that was the error was. The theoretical values, or what the theory was predicting using a perfect circle, was off by 8 arc minute with the Tycho's observations of the planet's orbits. Okay, so Kepler's first law is that planet follows elliptical orbits with the sun at one of the focus points. Okay. Number two, Kepler's law number two is that as a planet moves in its orbit, it sweeps out an equal amount of area in an equal amount of time. So for example, if I have planet being really far away or being in aphelion, and 1 month the planet is moving from this point to this point. So it is covering an area of this much. As this planet is getting close to the sun, or it's perihelion, it's moving faster. So it is covering this much of area. So let me call this area 1 in 1 month and area 2. But area 1 and area 2 are equal. So it sweeps out an equal amount of area in an equal amount of time. So in 1 month, you have a very short but very tall triangle. But then here, you have a wide triangle, but it's not very tall, okay? But they have the same area, so area 1 and 2 should be equal. That was the second law of Kepler. Third law is saying that the period of a planet increases at its mean distance from the sun raised to the power of 3 half power. In other words, the t squared in years should be equal to r cubed in AU, okay? Or should be proportional to it. There is a constant behind it, okay? So if you know the period of a planet and you square it, this should be equal to the average separation of that planet or a comet or object to the power of 3. And the average separation is in the units of AU, or astronomical unit. So AU is an astronomical unit, is the average separation from Earth and Sun, about 93 million miles, okay? And the period is just the period that it takes to do one complete rotation in years, okay? So there's this relationship that he found, and he put it as the third law of Kepler. So the t squared period to the power of 2 should be equal to the r, or the distance, average separation, or distance to the power of 3, or cubed, okay? So a geosynchronous satellite is one whose orbital period, or t, okay, is equal to 1 day. So in other words, it will take 1 day, 1 full day, to do one complete rotation around Earth. It's also important to note that the period of Earth is also the same. The period of the Earth is the amount of time it will take the Earth to do one complete rotation around itself, which is the same for this geosynchronous satellite. If such a satellite is orbiting above the equator, it will be in a fixed position with respect to the ground, okay? Because if you consider that, for example, if this is Earth, okay, and then let's say that this is the equator of Earth, all right? And Earth is doing one complete rotation in 24 hours. So the period is 24 hours. Now, if you have a satellite, let's say, okay, and this is the geosynchronous satellite, it means that it will have the same period, and it's doing this rotation around the Earth. Since it has the same period, which is the 24-hour, it will always be located above a certain area of Earth. It will always be located there. So the satellite are usually used for communications and for weather forecast. So it will be always in a fixed position with respect to the ground. Okay. So the second application is GPS, the GPS that we use pretty much every day. GPS satellites are not geosynchronous, okay, but they follow the Kepler's law. So, for example, this will give us the most precise location of objects on the surface of Earth. So they usually have the orbit of 12 hours, okay, and a point will get signal from different satellites. For example, this purple line is the constant distance from satellite number 6. Okay, the green one is the constant distance from satellite number 11. And then this red one is the constant distance from satellite number 2. But this point right there will have the most accurate information of its position because it's been observed with 3 satellites, okay, from different locations. In other words, we can use these information from the satellites to make the most precise, estimate of a location of an object. The motion of the satellites. The trajectory of a projectile fired from A towards B. So I have A right there on top of a tower, and then B is like right there. Okay, so kind of a launch horizontally. Okay, so from A towards B depends on its initial speed. If it is fired fast enough, it goes into a closed elliptical orbit. In other words, something like 3, 4, and 5. Okay, so it is important to know what your initial speed is, because the initial speed here will indicate if you're going in a closed path or if you're going in a path that is doing one complete rotation around Earth, or if you're not. So the projectile launch from A towards B trajectories 1 through 7 shows the effect of increasing initial speed. So if your initial speed is not enough, you'll end up hitting Earth right there. Okay, right here or right there. But if you have these, then you're doing a closed pass. If you go above, if you go, for example, to 6 and 7, then you might take a very much longer time, or you might even leave the Earth's gravity eventually. So, circular satellite orbit, and I think this is the part that I would like to stop and go over part 2 of the video. But let me go over this one last slide, and then we'll keep the rest for part 2 of the video. So circular satellite orbits. For the circular orbit, the speed of a satellite is just right to keep its distance from the center of the Earth constant. Okay, so this is very important. The speed of a satellite is just right to keep its distance from the center of the Earth constant. Okay, in other words, it's not going up or it's not going down. We're keeping it in a way that it has the same distance from the Earth. A satellite is constantly, freely falling towards the Earth. So it's constant state of free fall. So in other words, astronauts inside satellite in orbits are in a state of apparent weightlessness because they are falling with the satellite, okay? Just like a guy in an elevator, and the elevator cable is cut, and then what happens is that he will, in the elevator, he will feel that he does not have any weight, because if this is being broken, if the cable is being cut, or if it's not, then this guy is in a state of free fall. So he will, so in a free fall, you will have you feel no weight. So the W should be 0. Okay, this is the exact same thing that happening to the people in the space stations, for example, in a satellite, because they're constantly in a state of free fall. their apparent weight is 0. Okay, so this is the end of part 1. We'll continue with part 2 shortly.